chapter 11 about something called the derivative. And we're going to begin by talking about something called limits. And I'm going to start off by telling you, you're not going to get this immediately. This is not an easy concept because it's not like anything that you've ever had to think about before, because it's not algebraic, it's not geometric, it is a concept that is a little difficult for us to wrap our minds around in the context of math. But I think I can get you to the idea of a working knowledge of what a limit is before we go into the math by asking you, let's suppose that you have decided you're going to do field and track events, and you're going to train to do, let's say, the 50-yard dash. So the first time you do the 50-yard dash, you've been out of shape and not trained in a long time, so you don't do too good. You know, anybody want to hazard what they think they could run 50 yards in?
20 minutes.
Well, for some of us it might be 20 minutes. Well, let's say we start out and we can run it in, I don't know, we're really bad out of shape, so maybe a minute. Yeah, maybe a minute. Okay, and you're huffing and puffing at the end of that minute. But you're going to train. You're determined to do this. You've got 6 months before you have to run that race. So you run the next day. And you still, takes you a minute, 60 seconds. Then you keep training and you keep training, and a week later, you run your best 50-yard dash, and you can run it in 55 seconds. And a few more days pass, and you're still training every day, and training every day, and training every day, and you can run it in 45 seconds. So then a month later, you've been training for 30 days now, and you try to do your 50-yard dash, and you can run it in 30 seconds. Okay? You're doing good. And you keep running and running and running, and at the end of 3 months, you can do it in 25 seconds. But then the next day, it's still 25 seconds, and the next day, it's 24 seconds, and the next day, it's 25 seconds, the next day, it's 24 seconds, and the next day after that, it's 24 seconds, and it's 24 seconds, and it never gets any better. The day before the marathon, the best you can do your 50-yard dash in is 24 seconds. Okay? Can't you just keep training and eventually get it down to 10 seconds? Now think about this, running 50 yards. How far is 50 yards?
Half a football.
Half a football length. That's what I figured everybody would come up with because we were talking about football. So can you run halfway across football field in 10 seconds? You can try, okay? You can try. But could you ever do it in 5 seconds?
Usain Bolt? Usain Bolt probably can.
No.
Maybe. Maybe.
It has to be a very strong wind.
There would have to be a strong wind pushing you toward the halfway mark, okay? The idea here is that no matter what you want to do, whatever physical activity you want to do, you train at it, you work at it, you work on it every day, are you ever going to be able to get your time lower than some certain amount? Could you ever run the 50-yard dash in 5 seconds?
I mean,
I'm not. Yeah. Okay. You've got computers in front of you. I want you to Google it. What's the fastest time?
she did 5.20 seconds by Ben Johnson.
Okay. Ben Johnson ran the 50-yard dash in 5.21.
No, 0 seconds.
5.20 seconds.
So we can do it.
So eventually we could all do it because he did it. But can Ben Johnson run it in 3 seconds?
speak with. I mean, if he can, that's wow.
Yeah, he can, he needs to take over the role of Slash on the television show. He's about that fast, okay? So, when you've trained and trained and trained and trained and practiced and practiced and practiced doing something and tried as much as you can to keep improving, are you ever going to be able, if it's a physical activity such as running a 50-yard dash, are you ever going to be able to get your time below some certain point? Like 2 seconds for the 50-yard dash. Are you ever going to be able to get to that 2-second mark? Okay? That's the idea of what a limit is. Human beings have a limit to their physical potential. Race car drivers cannot run that lap in less than a certain number of seconds. The car just won't go any faster. Okay? All kinds of activities you can think of that try and practice as much as you might. You're going to have a place where your performance is going to level out and you've reached your limit. Okay? Now another idea, probably nobody in here has kids, but I remember when my kids were little, you had parents, and I'm pretty sure that they've said this in some form to you. If you do one more thing today, I swear I have reached my limit and you're grounded. Okay, that means you've really just pushed them to they're ready to skin you. They're so frustrated with you. Okay? They've reached their limit. They can't handle one more thing. That's the idea of what a limit is in math as well. So keep thinking about that idea as we go through. In previous courses, some with me, you learn to deal with what are called static situations. What is the revenue when you sell 100 items? We solve problems like that in finite math. How much interest is earned in 3 years? We solve problems like that in finite math. What's the equilibrium price at some given point in time for some set commodity that has a supply equation and a demand equation? What is the equilibrium price for that particular item that we're examining? We solve problems like that in finite math. In calculus, we're not going to deal just with static situations. We're going to deal with something called a dynamic situation. At what rate is the demand for a product changing? How fast is it changing? How fast is it increasing? How fast is it decreasing? We're talking about rates of change. How fast is a car moving after 2 hours? There again, that's a speed, miles per hour. And at the 2 hour point, how fast is it moving at that moment? When does the growth of population begin to slow down? So this is something that's changing over time. It doesn't stay fixed like a supply and a demand equation. It's actually changing depending on what point in time you are. What calculus is going to let us do is answer those kinds of questions, and remember, as I said, those all deal with something we call rates of change. Something that in your mind, the word rate of change needs to trigger the word slope. Slope is a rate of change. If I ask you in here all throughout the semester, what is a slope, I don't want you to tell me it's rise over run. That was a neat way in algebra to remember how to do it because it's the up and down distance over the back and forth distance. But slope is a rate of change. How much does this value change based on a certain amount of change in the value in the denominator? How much does y change based on how much you changed x? It is the slope of a line, but not just lines have slope. Curves also have slope. They have a rate of change at a given moment in time. Not everything increases or decreases linearly. There are other kinds of equations like polynomial equations, like equations with radicals in them, rational equations. We're going to talk about something called a logistic growth or logistic decay function. We're going to talk about exponential growth and decay, which is related to the logistic. So the key idea in calculus is the concept of a limit, and that's why we start off by studying limits. If you feel a little fuzzy and a little shaky through the first part of this chapter, just keep after it. Don't give up. Keep working at it. I'll see the light bulb come on sooner or later, because it will suddenly dawn on you oh, that's what we're doing. It may not dawn on you exactly what a limit is until we get toward the end of the course. But you'll be able to find limits based on your kind of intuitive knowledge of what one is. So this is our first example, and this is in your notes. What happens to f of x is equal to x squared when x is a number very close to, but not equal to, 2? Close to, but not equal to. Now let's just get it out of the way right up front. What is f of 2 if f of x is x squared? 2 squared is 4. Okay? Don't be afraid to shout it out, because I'm not going to ask you any hard questions. Not today. Okay? But suppose for some reason, there is no math reason in this case that it couldn't happen, but suppose for some reason that we can't actually plug 2 into that equation. Suppose we're not actually allowed to put 2 in. Could we figure out what it ought to be at 2? And the answer is yes, we can. Now, you probably don't want to think about doing all these calculations in your head. I don't either. I can't square 5-digit numbers in my head. I just can't. It doesn't work for me.
He's like, oh, you
Okay.
I don't care what you say.
I thought the technology and for change, I won. Okay, on the calculator, what we're going to do is we're going to go to y equals, and I'm going to clear out the equation that's in there, and I'm going to type in x squared. So this is my f of x. It's at y1. Then I'm going to go to the window, to the table set. Second window takes you to your table setup. If you had me in 1630, and probably this fits also, she probably showed you how to do this. Go into your table setup and set your independent variable to ask.
Want that table started, negative grid?
It really doesn't matter where the table starts, because it's not going to show us anything. So it doesn't matter what table start is or what the increment of the table is. Go down to independent and click on ask. And then click OK or enter. And then go to second graph, and you should see a blank empty table. Okay? Now remember, y1 is x squared. Now what we want to do is we want to approach 2, but we can't actually plug in 2. Okay? So this is how we're going to do it. We're going to start and approach 2 from a number less than 2. Close to, but less than 2. Is 1.9 fairly close to 2? Okay, then we'll type in 1.9 and see what's going on. And it says if x is 1.9, then 1.9 squared is 3.61. Now that's close, but we could get closer. We could go from 1.9 and move a little closer to 2 by going to 1.99. Okay? Well, 1.99 squared is 3.9601. So 1.9, 1.99 is closer. We can move still closer and yet not be 2. We can go to 1.999. So now we're closer to 2. and 1.999 squared, it says it's 3.996, but actually if you put your cursor on it, it's 3.996001. Okay? Now we can get closer yet again. We can have 4 nines. And again, it gives us most of the digits, but not all of them. So that's 3.9996001. And we can actually even try to get closer than that. Even though it's not in the table, using the calculator, we can try to get even closer. But something interesting happens. Now you saw me enter 1.99999. The calculator says that's 2. Well, that's because it can't show me more than 5 digits in a decimal place in that column. So since it can't show me all the digits, it rounds it to the closest number, which 1.99999 is just really, 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 really close to 2, right? And it says that it's 4, but the truth is it actually squared 1.99999, and it got 3.999960001. So I want to look at what we're actually doing here. We started out sort of close to 2, but then we moved a little bit closer, and a little bit closer, and a little bit closer, and a little bit closer. And I could keep on going. I could keep adding 9s. And the calculator would hold it up to about 14 decimal places. And after that, it'll say, no, you're done. I'm not doing that much. But, okay, you can see what's happening in the X column, right? We're getting closer and closer and closer and closer and closer and closer to 2. But look what's happening in the Y column. We start out not really very close to 4. You know, 3.61 is, it would round to 4 if we rounded to a whole number, but that's not really close to 4. But as I add more 9s and get closer and closer and closer to 2, what's happening to the Y value? What is it getting closer and closer and closer to?
To 4.
To 4.
Yeah.
Okay? That's the idea of what a limit is. You're putting in your best effort to get to some number that you know you're never going to reach, and the result is going to be some other number that you're getting really close to, but you can't actually touch. You can't get there because you can't go and be 2 and be squared and turn into 4. Okay? So don't try to make more out of this than there is. If you think this answer was obvious, good, it's supposed to be. Okay? Now we can do the same thing. Remember, we only approached from 1.9. We could also approach from 2.1, from a number bigger than 2. And we could kind of back into 2. So we could start out with 2.1 and 2.01, 2 and 1/10, 2 and 100, 2 and 1,000th, 2 and 1/10,000th, 2 and 100,000th. And notice again, when I put in more digits than the calculator could actually display, it rounded it off, but it really did recognize that I put in 2.00001. So again, as I'm letting X start somewhat close to 2, but a little more than 2, and approaching 2 from what's called the right, because I'm approaching it from above 2, what happens is I get closer and closer and closer, but I'm still not plugging in 2. And if I watch what happened to the y as I got closer and closer, when I started out at 2.1, I wasn't all that close. So the answer isn't all that close to what I think it ought to be. But as I get closer and closer and closer and closer, the result gets closer and closer and closer to the value of what 2 squared would be, which would be 4. That's the idea of a limit. And this is what we're going to call the table method for finding the limit. And on your test, you can always use the table method to find the limit of the function at a number just by starting out at 1/10 below it and 1/10 above it and kind of marching in on it, trying to cage it up or box it in until you can get a really good estimate of what the value would be if you could plug in that number. Now I picked one in this case because I picked one that we actually could plug into. We don't know why we're not allowed to, but we could plug in 2, and we know that 2 squared is 4. But what if this had been 1 over x minus 2? What if the function had been 1 over x minus 2? Could we have plugged in the 2? No, because we would have had an undefined expression. Now something odd happens if we try to do this with 1 over x minus 2. This is not in your notes. But I'm going to show you what happens if we try to do 1 over x minus 2. Now, if I try to go a little above 2, at 2.1, 2.01, 2.001, 2.0001, these numbers over here are actually the numbers. If we try to approach 2 from above it, what seems to be happening to the y value? Is it coming to a number? No. If I plugged in, looking at the pattern that you see in Y1, if I plug in 2.1, 2, 3, 4, 5 zeros and then 1, what do you think is going to come out? Let's try it and see. 1,000,000. Every time I put another 0 between that decimal and that 1, it adds another 0 to the result. So if I were to ask you, as x approaches 2 from a number above 2, or from the right, what happens to f of x, what could you tell me? Just in words, no mathematical symbols, just in words. What is happening to 1 over x minus 2 as x gets closer and closer to 2?
It's increasing.
It's getting bigger and bigger and bigger and bigger and bigger. It's increasing without bound. Okay? The language of calculus says it's approaching infinity. Okay? Because infinity means it's getting bigger and bigger and bigger and bigger and bigger. Okay? I can do the same thing that we did a minute ago with the 1.9. I can start out 1/10 away and then go to 1/100th away. And then I can go 1.999. That's pretty close to 2. But 1.9999, and it's even closer. And closer. And closer. And notice that even though those numbers over there are in scientific notation, that just means it's -1 followed by 6 zeros. I'm sorry, 5 zeros. Looking at the wrong one. That's -1 followed by 6 zeros. So what's happening to y as I got closer and closer and closer to 2, but I came at it from less than 2? Tell me in words, just plain old English words, what's happening to the y value of 1 over x minus 2? It's a little harder to say than the positive side was, because the positive side was getting bigger and bigger and bigger. Only now it's negative.
Yeah.
Going to negative infinity.
It's going to negative infinity. What it's actually doing is it's getting smaller and smaller and smaller and smaller, which, you know, the number is getting more zeros in it, but it's a negative number, which means it's smaller, really. It's getting further from 0. Okay, so it approaches negative infinity. Everything isn't going to converge to a single value. 1 over x squared, or x squared does, but not 1 over x minus 2. They go in, the two sides go in different directions. So if I use 1 over x minus 2, and I look at it from the left, it goes to negative infinity, but I look at it from the right, it goes to positive infinity. And what eventually you're going to learn in this class is the limit for 1 over x minus 2 as x approaches 2 doesn't exist, because it doesn't come together. It doesn't come in on a single number. And that's because you really can't plug in 2. This function can't be evaluated at 2. So the phrase x approaches 2 from the left in the language of calculus is written as x with an arrow showing that it's going to the number 2, and then the little negative sign up there like an exponent means it's approaching 2 from the left of 2. And what we're seeing happen here, this is a graph of that function, and if x approaches 2 from the left, that means it approaches from the left of the number 2. And in other words, it approaches from numbers less than 2. So associate left with less than. And as x approaches 2 from the right, we say that x approaches 2 from the positive side. Okay, the right is positive, the left is negative. The left is less than, the right is a number more than. Those are what we call expressions used to write one-sided limits. So the limit, as x approaches 2 from the negative direction, is written the limit, LIM, over x, arrow, the number 2, which is what it's approaching, with a little negative sign, and then you put equals 4, because that's what it's approaching. It's getting closer and closer and closer. The y value that's coming out as we move closer and closer to 2 is getting closer and closer to 4. And then the limit as x approaches 2 from the right would be written limit, LIM, over x, arrow, 2, and then the positive sign of that function would then also be 4. Because as we approach from the left or the right, it's coming closer and closer to the actual value, f of 2 squared. And that's what's shown here. Okay? The two-sided limit, not coming from the left or the right, but coming in simultaneously from both sides, simply doesn't have the plus or the minus after the 2. It just says as x approaches 2. And as long as that limit actually comes to the same number, then we write down what that number is. Then in the other example I showed you, if we tried to do the limit as x approaches 2 of 1 over x minus 2, we would write after that one does not exist. Because the left-hand limit and the right-hand limit went to different places. They didn't come together. Now, this is the calculus book definition. I do not expect you to memorize it. I don't even particularly expect you to be able to read that and make any sense of it. But everything that I just went through trying to explain to you how to look at it, that's basically how calculus sums up what we said. Okay? I'm not going to ask you to quote definitions and theorems to me, but that's the definition in the book. It says, as x takes, takes on values closer and closer to, but not equal to a on both sides of a, then it reaches a limit. And you can take values as close to L as you want to just by making more and more and more decimals on either side. So keep in mind, here's the difference. The definition of a limit describes what happens to the function, the y value, as x gets closer and closer to or near to, but not, but not equal to that number. It's not affected by how or even whether you can plug in that number. You can still try to take the limit. Now, as we saw in the second problem, it also says that you can approach two different numbers because then that's not a limit. A limit has to be going to the same place. It has to be leveling off at the same number. It can't be going to two different places. There's no limit in that case. So here's another example. Find the limit of g of x as x approaches 2. And look what's in the denominator. Can x actually be 2?
No.
No. Cannot. Now, if I don't tell you any more about that problem and we just put it in the table form, do you think it's going to do the same thing 1 over x minus 2 is doing? Going down to negative infinity out to positive infinity. Kind of seems reasonable that it might. Okay? But it won't. I won't tell you why it won't, but let's see what it does do. I'll tell you why it doesn't do that after we've investigated it. And I've already made the table. So you can do your calculator. All you do is enter this function, x raised to the 3rd power, subtract to 4. But if you plug in 2, it says there's an error. Now, why is it that when we did 1 over x minus 2, it went down forever and it went up forever? Remember when we did 1 over x minus 2, if we approach from the right, the numbers got bigger and bigger and bigger. And if we approach from the left, they got more and more and more negative. Why isn't that happening here? Because we've got x minus 2 in the denominator, it can't be 2. Why are we not? Can you simplify that function?
Yeah.
You can simplify that function.
I got my squared times y.
That's right. Because it is f of x is equal to x cubed minus 2x squared over x minus 2, which you can, and remember we reviewed factoring. There is a common factor here of x squared. So f of x is really the same behavior as x squared, but we have to make the note that x can't be 2 because in the original function it can't be. Even though this is a simplified version of it, and we can simplify it by factoring and canceling, in the original function f of 2 was not defined. So it can't be defined for this number either. Okay? And that's what this is showing here. By factoring the numerator, you see that g of x simplifies to g of x equals x squared, provided that x is not equal to 2. Now there's another way to actually try to find limits. You don't have to do it using the table method, although that's a pretty simple method to use because once you get the idea of how you're putting in your x values, then it's easy to figure it out. But you can also do it this way. While we still have this in here, the correct function this time, thank you for correcting me, we can actually go to the graph and we can trace on the graph. So I'm going to start out by hitting second trace, going to value because I have a specific place that I want to start at. I want to start at x equals 1 because 1 is definitely less than 2. And then I'm going to trace from there as close as I can get to 2. I'm pretty close to 2 right there. Notice that y, as I got closer and closer to 2, got closer and closer to 4. But now I've jumped over 2. So if I try to start from, let's say 3, and then trace backwards, you can see that I'm getting closer and closer to 4, but I've already jumped over 2. So what I'm going to do, and this actually, I'll show you in the slide how I did this. What I'm going to do is I'm going to hit the zoom decimal button. Zoom, and I'm going to choose number 4, decimal. We use that screen a little bit in Math 1630, but we'll use it a little bit more here because it lets us actually see the place where x can't be 2. So I went to zoom decimal. And then what I'm going to do is I'm going to adjust my window because I know I don't need to see negative numbers. 2 is not in the negative numbers quadrants. So I don't need to see negative numbers for x, so I can start it at 0. And I also don't need to see the negative numbers for y because this graph never goes below the x-axis. So I hit graph again. And you don't see anything remarkable yet. But if I go to my mode button and change from connected to dot mode so that it doesn't try to connect everything up, and hit graph, all I see is the dots. So I still have an issue because I'm trying to see this screen right here. So the way that I actually get to that screen is I go back to my window, and one of the reasons I'm not seeing it is because it's too spread out. So I'm going to go down here and make the window go higher. I'm going to multiply that 3.1 times 3. And you see what I see at x equals 2. You see a hole, right? Now, it isn't normal to see that hole because that big hole is not a big gaping hole. It's a single value. You would never be able to see it with your naked eye. But your calculator is trying to show you that it's not there. And if I trace, and I'm coming at it from above or from the right, if I trace closer and closer and closer to 2, all right, I'm pretty close there. I fell in the hole. And if I go to the left, and I go down to 1, and then I trace, I get closer and closer and closer to 2. So that's pretty close, 1.95. But if I hit dead on 2, it doesn't give me a y value because I fell in the hole. Okay, that's one way to think of it, is you just fall in the hole if there's one there. And that screen there is there because anytime you want to see a specific y value for a specific x value, you can always hit second and the trace button and choose value and type in whatever number for x you want, and it'll tell you what the y value is on the graph, as long as that x number is within the numbers you see on the screen. So I couldn't pick a number like -2. That wouldn't work because I'm not showing you where x is -2 on the screen. So in summary, you can actually find a limit 3 ways. First way is algebraically, which means you're going to need to factor or something like that. Second way is using a graph. Either draw it by hand, which I know you're not into. Most people aren't anymore. Or by using a graphing calculator to draw the graph. Or the best way for most of us is using a table. And the calculator makes it easy to build that table. Let's look at another couple of examples. Determine the limit as x approaches 2 for h of x if the function is h of x equals x squared as long as x isn't equal to 2. If it is equal to 2, then its value is 1. This is a piecewise function. And I included this one because I want to show you how to enter a piecewise function into your graphing calculator. So we're going to clear out what's there. And this is how you enter a piecewise function, which you're going to need to do occasionally in here. So this is going to be recorded and kept for you. The way that you enter a piecewise function, where you've got 2 different rules, depending on what part of the domain you're in, is you put in the first rule, which is x squared, and then immediately in parentheses after it, just like it was a multiplication problem. Right after that first rule, you put in what its domain restriction is. This says x can't be 2. So we type the x, and then second math is where you find all your inequality signs. So x, and we're going to choose option 2. X does not equal 2. And close it. And we type plus sign, and we enter the second part of the function, which is the number 1, but it has to be in parentheses. And its domain restriction is if x is 2. So x is equal to 2. Okay? Now I'm going to leave it on the same window that we were before, because if this works, we should still see that hole. And you do still see the hole. The only thing is, it's trying to connect up these 2 pieces to the undefined value at 2. And there's not a good way to make it not show you that. But if it weren't for this part that's not really part of the graph, because it really isn't. Actually, if I ask it, what is the value of 2? That's what it's trying to connect up. It's trying to connect the rest of the graph to the point 2, 1. So that's what those 2 little jagged looking lines are. So these are the 2 pieces. Now looking at that from the graph, we're trying to find the limit as x approaches 2 of h of x. What is it? As it's approaching, it doesn't have to be 2, because when it is 2, the y value is 1. But as I approach 2 from the left and I approach 2 from the right, What number is it getting closer and closer to?
0 or 1.
Let's trace and see. Let's start out at 1 and trace closer. Ah. What number is it getting closer and closer to?
2.
Now, if I hit one more time, it's going to go on 2.
No, it won't. Wait. Maybe.
What's it getting close to? What is the Y value getting close to? 4.
But it can't equal 2.
Oh, but it can this time
Oh, okay, the 1, yeah.
because of the 1.
Gotcha.
Okay?
I thought it was-
So that function is approaching 2 as x gets close to 2. But when it gets to the value 2, it jumps down and puts one more little point in there that's not even on the graph. Okay? So the same limit is what we've been having before. The limit in this case is still 4. Because it's still essentially behaving the same way as y equals x squared. Okay? Now I'll finish this up, and y'all can finish filling in your notes about limits, and then I have an activity for us to do next time. So I'll finish the recording for this. Y'all watch the recording, finish filling in your section 1 notes. If you have questions, write them down in your notes, and I can go back over a problem with you if I need to. But then I'm going to bring an activity in that will help you work with continuity, which is what we're going to talk about next time.
So we don't have to worry about everything tomorrow.
Excuse me?
We don't have to do it tomorrow. It's going to do tomorrow. So we just don't worry about it tomorrow.
You do not have to have homework for 11-1 done until, I thought I changed the date, but I will change it again. The homework for 11-1 and 11-2 isn't due until Sunday night.
It just said the class activity.
Yeah, but it's not gonna be, because I was mistaken when I put it up there. I thought it went with this, it goes with next class. So it's gonna be due on Friday. Y'all have a good day, and I hope we have another room.